Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll study about rectifiers, single phase rectifiers and specifically half wave single phase rectifiers with resistive and inductive loads and RLE loads. So in the previous lecture we learned about filters a bit, then we learned about inductors and capacitors and also half wave rectifier with purely inductive load. Now what we learn with a resistive and inductive load and also with a RLE load. Okay, and we'll do few questions on this particular topics. So we will continue with the whatever concepts we learned in the previous lecture in this lecture. So here I have a single phase half wave rectifier, and always remember a single phase half wave rectifier can be one pulse converter, it can never be two pulse converter. Supply voltage is this, okay, and my rectifier is something like this. So we'll mainly focus on the controlled one, because for the uncontrolled one you can do it, right? You can easily do it without the that triggering angle. We can use the triggering angle as alpha minimum. Now what is the example of this RL load? So if you want to understand practically, when does a RL circuit is practically used. So if you watch in your homes, you have that tube lights, right? White tube lights. So those tube lights are also sometimes assumed as RL loads. Okay, those tube lights are assumed as as RL load. So this is one of the example of a RL load. Now obviously we understand the forward blocking mode, like for a region in which the SCR will be forward blocking mode. This can change later on because here we have inductance, but still to start off with, we start off our analysis. First we decide the forward blocking region of forward blocking mode, then we go along and see what changes we need to make. Okay, so here initially my IL0 minus was 0, hence there is no change in initial current, so VL0 minus will also be 0, and as IL0 minus is also 0, that means my VR0 minus will also be 0. Okay, so everything is 0 on the right hand side, so my VT will be simply equals to my VS. VT will be simply equals to VS. Okay, so VT is equals to VS. Now what can I say about the VT waveform? VT waveform will be sinusoidal. If VT waveform is sinusoidal, you can draw it just in rough. So this will be what? This will be the region of forward blocking mode. This will be region of forward blocking mode, right? And in this region obviously we can never control, even if there is no voltage, you can never control it. Okay, so we have no control over in this region anyways, but I will say you this region can get expanded as well. Can't control in this region, right? It's a no control. Okay, now what can be my alpha minimum? So here my range of triggering angle can be from 0 to pi, right? 0 to pi. So this is my alpha minimum. So if I replace my alpha to 0 degrees, then obviously it will become a diode circuit. Okay, it will become uncontrolled. So this is the region of forward blocking mode. Now what is happening, like from 0 to alpha, I am not turning it on, right? I'm not triggering it. So what will happen? The current will be 0 because SCR is off and the current through the SCR can only flow in one direction. So IS equals to IT equals to IO equals to 0 amperes. So VO equals to simply 0, right? Because initial voltage was 0 and drop to the resistor is 0, so inductor voltage will also be 0. V equals to IO into R plus VL, which will be 0 because VL is 0 and IO is also 0. And my VT is VS that I already established in the previous slide. And obviously here I can observe that VT is greater than 0. Hence my thyristor, right? My thyristor will be in forward blocking mode. Thyristor will be in forward blocking mode. Okay. So this will be the case, like here 0 ampere. So current will flow. Okay. So now when we trigger this here, so when we just trigger this here, so at omega t equals to alpha, SCR is triggered. So SCR will obviously turn on because it has some positive voltage, right? Anode to cathode voltage is positive. So SCR will turn on. Hence, my VT is 0 volts. Okay, VT is 0. My VS is simply equals to, so not VS, sorry, VS is same only. My VO will be simply equals to VS, right? VO will be VS. And one thing to remember, initially the current is 0. Hence, like what will happen, there is no impulse voltage because VS is finite, right? VS is finite. There is some finite value, sinusoid like just 0.001 or something like that. So there is some finite value. So what can I say? If this is some finite value, then I can say is that IL 0 plus will be equals to IL 0 minus, because no infinite amount of voltage is getting applied across the inductor. Hence this will be only 0 amperes of current, right? Because IL 0 minus was 0. So like current will increase obviously as this VO is equals to VS. Hence my VL will be what? VL will be, so I am assuming that you already know transient, right? So I'm not explaining what do I mean by this. So if you have watched my marathons or if you have watched Himanshu Agarwal, there you will explain on this, right? So I'm assuming you are understanding on this. So my VL will be equals to VS. So VL 0 plus will be equals to VS 0 plus, which will be greater than 0, right? Which will be greater than 0. Hence, as it is positive, that means what? That means my DIL by dt is greater than 0 because VL is equals to DIL by dt is greater than 0. That means my IL is obviously increasing. IL is obviously increasing, right? So here what is happening actually? IL is increasing, right? The energy stored across the inductor is increasing. That means what? Energy is getting stored in the inductor. Inductor is energizing. Okay. If inductor is energizing, that means the power flow, right? The power flow, direction of the power flow is from source to load. Because this is my load, right? This is my load. So this thing, right? This thing is my load. This thing is my load. So here power is flowing from source to load. So here, right, this is what I can say. Power is currently in this from this alpha to at least pi, because after pi what is happening? After pi what is happening? This will basically close, right? This it will be in reverse blocking mode. Now, interesting fact here is, although inductor will obviously want it not to be in reverse blocking mode, it will still keep the SCR on. But up until R, at least I can safely say that this will be at least like charging. Why this will be charging? Why will the power from source to load will flow during this alpha to pi? Why is that the case? Because if you observe, right, I will just take this on the right, like next slide. So here if I just copy the cases, right, copy the cases. Okay, so in this case, right, in this case my Vs is positive. If I draw the circuit, if I just take the circuit, right, Vs is positive in this from alpha to pi, right, omega t alpha to pi, my Vs is positive. Vs is positive. Okay, and my Is it positive? Is is positive. Yes, right. Like what can happen to Is? Is can either be 0 or positive. Can it be negative? Can Is be negative? Tell me. Just pause the video. Tell me, can Is be negative? No. Is can never be negative. Why? Because I have a SCR connected, and SCR is a unidirectional device. It can flow current only from the anode to cathode. It cannot flow current from cathode to anode. If it is practical, obviously small leakage current will flow. That I am ignoring. Okay. So Is can never be negative, right? Hence, what is the product of Vs into Is? That is the instantaneous power, right? Vs into Is is the instantaneous power. That is my Ps, which is greater than 0. That means what? It is positive. That means my source is supplying the power. Okay, that means my source will simply supply the power. That's it, right? That was a simple case. That's why I will go until alpha to pi, and then what will happen? The polarity will flip instantaneously of the source. Not instantaneously, but like it will go, like let's say it was from at 0.1 at omega to t equals to pi, just less than omega t equals to pi. Then just hold on, I will just check if everything is recording. Yeah, everything is recording, fine. So yeah, and just at omega t equals to pi plus, okay, just after omega t equals to pi, it will go to minus 0.1. So this polarity has flipped. But remember, right, inner current cannot change instantaneously unless a impulse voltage is applied. And what is a voltage? This is some very small voltage, finite voltage, not infinite voltage, 0.1 volts. So inverter will never change its current instantaneously. So that like let's say 1 ampere of current was flowing at pi minus, and that same 1 ampere of current will flow at pi plus. Obviously, then what will happen? It will reduce a slow amount. So why it will reduce? So for that I will understand this case 3. So in case 3, right, what is happening? The SCR will try to turn off, but inductor will not allow SCR to turn off. Inductor, if I have some, yeah, inductor will not allow SCR to turn off. Okay, inductor will not allow SCR to turn off. So inductor will not allow SCR to turn off. Now why is it the case? Because it will try to flow that constant current. So here what will happen this time, right, my Is can never be negative again. Is has to be positive. Okay, and that same amount of, almost that same amount of current is flowing, and Vs is what? Vs this time, right, is negative, because after pi, right, after pi the source becomes negative, right? Very small amount, but still it becomes negative. So if Vs is negative, what does that means? That means my Vs into Is is less than 0, or what I can say is power Ps. Vs into Is is less than 0. That means what? That means flow of power, right? Like if I just copy this in the next page, that means power is flowing from load to source. Okay, power is flowing from load to source. So this is the flow of power. Why from load? Because if you observe, right, what is VO? VO is negative, right? Because VS is equal to VO because SCR is still on. So as SCR is on, okay, due to the inductor, it is keeping the SCR on. Hence, my VO will be equals to VS. VO will be equals to VS. And like if you want to answer this, right, so my VO is equals to VS and less than 0. And what is VO equals to? VO equals to IO into R plus VL. Okay, you can understand from here as well. And what is VL? VL is VO minus IO into R. Okay, and this is positive, right? This is high positive number, positive and high. Okay, because like IO is what, let's say 1 ampere current, and RO will be 1 ohm only. Okay, and VO is what? VO is some negative value. Negative. So I'm subtracting from a negative value another negative value, right? Because this thing is positive and I'm subtracting it. So overall I will get a negative value only. So VL, I can safely say VL will be less than 0 volts. Okay, VL will be less than 0 volts. That means my DIL by dt oh no, that is bad. Okay, that means my DIL by dt, right? DIL by dt DIL by dt is basically less than 0. That means my inductor current will basically reduce. It is discharging, right? Simply I can safely say it is discharging. Okay, so this is the case basically. So it is de-energizing. The current will reduce now because DIL by dt is less than 0, so current will reduce. Okay, and power is flowing from load to source because my VO is negative. So I hope you understood this simple concept now. And until when it will turn off, like that angle, right? Is computation of that angle is very difficult. I will tell you how to compute that angle. You have to use some other methods, but we will assume that the conduction stops at extension angle, that is beta. Conduction stops here. Okay. And another important point to note here is that if I observe, right? If I observe one thing, that when it was charging, the thing was that, okay, here did I write that? Yeah, this thing that I wrote, right? What is my voltage? Voltage is equals to Vs, supply voltage, right? It was almost equals to 0. Okay, so my voltage, right? My voltage, like if I assume this as steady state, this was at t equals 0 plus. If I assume when this was charging, okay, when this was charging here, this is also alpha equals to pi. So we'll just copy this case. Assuming at steady state the current is some current is flowing, right? So what can I write as my VL? So when it was charging or energizing, I might say, my VL was equals to VO minus VR, right? You agree with this, right? You agree with this. Like VL will be simply overall voltage minus VR. And in this region, right, VO is positive. VO is positive. Okay. And VR is also positive. So I am subtracting from a positive number another positive number. So overall, right, this will be low. Overall, this value will be low. Let's say like what VO, let's say VO is 4 volts and VR will be some 3 volts, right? So assume VO 4 or VR 2 volts. Okay. So if that is the case, what will happen? Overall, my VL will be 2 volts. Okay. Overall, my VL will be 2 volts. Now let's go to the second case, case 3, right? Here, if I assume, like what is my VL this time? What is my VL? So my VL is equals to VO minus VR. This time my VO is something negative, right? Because VO is simply VS. Here also I should have written it. VO is simply VS, right? VO is simply VS. So this time my VO is negative. So let's assume like again VO to be some negative, like it's same at the same point. VO is let's say -4. Okay, and VR will always be positive because current can only flow in this direction, and my like polarity of VR, assumption of VR is like this, right? This is my polarity of VR, this is my polarity of VL. So this assumption will always be there. This is my polarity of VR, written here, right? Here I written VR and VL. Okay, so here my VR will be, VR will always be positive. I will assume VR to be 2 volts. Now can you tell me what is my VL? VL is -6 volts this time. So this is negative, but the magnitude of VL during discharging is greater than the magnitude of VL during charging. Okay, so the magnitude is greater, right? So what will happen is it will discharge faster because the magnitude is greater. So dIL by dt during discharging is faster. So at a very high rate the current is changing, right? If at a very high rate current is changing, what is the steady state? The steady state will be voltage across the inductor is 0, and obviously at steady state the SCR will turn off, hence the current will also be 0. So at steady state the SCR should turn off, right? Current will be 0, then all current will not change because supply is always changing. To reach to the inductor steady state, like it is reducing, right? The current is reducing. I know dIL by dt is negative, so current will reduce. It will reduce until what? It will reduce until IL equals to 0, because then only SCR will be off. At IL equals to 0, SCR will be off. Why SCR will be off? That we learned in the previous lecture. Okay, so the charging, the magnitude of charging is lower than the magnitude of discharging, hence it will discharge faster. That means, what can I specifically say here? I can specifically say that my charging time will be greater than discharging time. Okay, so this is one conclusion that I can get to, okay, without even knowing the values. Okay, without knowing anything, I can conclusively say this: the charging time will be more than the discharging time. Okay, this one thing I can conclusively say. Okay, discharging time. Now let's go to the case 4. Case 4 is also very easy. Basically what will happen at beta, the current becomes 0. If the current becomes 0, SCR instantaneously moves into reverse blocking mode. Why SCR moves into reverse blocking mode? Because if the current is 0, right, current is not changing anymore, current is not changing, hence VL 0 minus is not 0 minus, VL pi, this beta minus, right, VL beta minus will be 0, VL beta minus is 0, so my VO also will be 0, so VO will be 0 in this case. Okay, and what is my anode voltage? Anode voltage is Vs, right? So my thyristor voltage, right? Thyristor voltage is Vt is equals to Vs simply. So thyristor voltage is Vs, and my cathode voltage is 0. Sorry, yeah, anode voltage is Vs and cathode voltage is 0. So overall thyristor voltage is Vs, and I know Vs is less than 0. If Vs is less than 0, basically it will go into reverse blocking mode, right? Reverse blocking mode, and SCR will be naturally commutated due to the load and the supply. Naturally commutated. So this will be the basic things. This will be the total analysis from 0 to 2 pi, but again, right, from 2 pi to 2 pi plus alpha, again it will be off. Again I will turn it on, trigger it at alpha, and this cycle will fall. Okay, so let's understand the equations now. So these type of equations won't be asked, simple thing will be asked. I will explain those things later on, don't worry. So if you have studied AC transient already, you know that I of t can be explained as a steady state form of IO and a transient form of IO, right? So how do we write this steady state form? We write the steady state form like this. At steady state, this will be simply a sinusoid response. So Vm by Z sin omega t minus phi, it is tan inverse omega L by R, and Z is this, right? This thing I hope you already know. Okay, next, this, if there are two cases, if my L by R, if my time period, right, if my time period of the waveform T is very greater than L by R, what will happen? There will not be any transient, because this will like settle in very low amount of time with respect to the time period, right? This will not take much amount of time to settle. So okay, so all these things, if you don't understand, please you have to go through the AC transient part. But I can say the condition, right? Condition is what? Condition is basically, I can flip these things. F has to be less than R by L. Okay, if my frequency is much lower than the ratio of resistance and inductance, then I won't have any transient. So I won't have any transient, right? No transient. I can say that I will not have any transient because it will have enough time to settle. So I will only see this steady state response. But if there is some transient, right, how will you find out? So you will find out this value of A, right, due to this transient, like this. You put omega t equals to alpha. So what do I know? At omega t equals to alpha, I know this, that my IO of t is 0 amperes. My IO of t is 0 amperes. So what can I say? That I can put this 0 in this equation, right? In this total equation, I can put this. So IO of t is equals to 0. So 0 will be equals to Vm by Z sine omega t minus phi. So not omega t is equals to alpha, right? Omega t alpha minus phi plus A e raised to power minus R by L. Like omega t is alpha, right? So t will be what? Alpha by omega. Alpha by omega. So my A will be what? A will be simply equals to Vm by Z sine. I can put this on the left hand side. So this will be sine, yeah, and there will be a multiplication as well into e raised to power R by L alpha by omega phi minus alpha. Okay, so this will be the values of like, because I have subtracted it, so this become negative here. So now, right, now what you can do is you can also find the value of beta as well. You can also find the value of beta, or like you can directly write this as negative. Okay, if you want to write this as negative, that also, okay, sorry, that also you can do. You can write this as negative, or you can flip the angles. So my IO expression will be just this, right? IO expression will be just simply this. Okay, now what about the beta angle? How do you find out beta? So how do you find out beta? So for beta, right, you just put in the equation that at beta what is happening? IO of t is again becoming 0. So at omega t equals to beta, my IO of t should be 0. So I will exactly do that. I will put this here. So my t will be what? T will be at beta by omega. T will be at beta by omega. Okay, so t is at beta by omega. So you might say, how will you solve this? Because here, right, I have a sinusoidal and here I have a normal equation, right? Normal, this exponential equation. How will I solve this? You solve this using numerical method. Don't worry, you don't need to solve this in examination. Solve if you have studied mathematics from me, right? In the last chapter I have explained like a few examples where the equation is not polynomial. This is a non-polynomial equation. This is a transcendental equation, and to solve transcendental equations you need the help of numerical methods. Numerical method. Okay, don't worry, that won't be needed here. That won't be needed here. Okay, that won't be needed. Because like in examination all, we don't have time. This numerical methods takes more time, and computers can do it better than us. Okay, so like, but they will give you the extinction angle. But like how do the computers solve? They solve it using numerical methods. Okay, so these are the waveforms. Okay, from 0 to alpha, the source is turning on. Then like from 0 to alpha, the source is off. Hence the output voltage will also be 0, because inductor voltage initially is 0 and current is 0. So the drop across the resistor will also be 0. So this will become Vm sin alpha. Then this becomes positive. Then at this point, right, at pi, the like as the output voltage is equals to the input voltage, so as the source becomes negative, the output voltage also becomes negative. But if you observe here closely, this time, right, this is, let's name this time as Tc, or I will write this as omega into T charging. I have deliberately drawn it like this, that I have drawn the discharging time lower, because it charges for more amount of time and discharges in lower amount of time, because the voltage is the discharging rate is higher. Okay, discharging rate is higher, so it discharges at a faster time. Okay, so like if you have observed this beat, like from pi to beta, that is beta minus pi will be lower than this pi minus alpha angle. Okay, so I can say here my beta minus pi will be lower than pi plus alpha. So like this will give you one simple basic equation. This will not be plus, this will be minus. This will be alpha plus beta is less than 2 pi. Okay, so alpha plus beta should be less than 2 pi, which is a basic common sense, right? So it can, like overall this charging and discharging, overall this thing, right, current cannot be greater than 0 for more than 2 pi, because 2 pi is the maximum period, right, of a waveform. So it cannot be more than that. So what is the thyristor voltage? So from 0 to alpha, it is in the forward blocking mode, so obviously it will block the supply voltage. Then from alpha to beta, the SCR is on. There is no current, like current never goes to 0, so SCR will always be on. And then from beta to 2 pi, the SCR will be off again, and it will again be in the reverse blocking mode. And this time is known as the natural commutation time, due to the inductor provided a natural commutation as the inductor fully discharged. Then again this time is forward blocking mode, and then this cycle repeats basically. What about the current? So this is supply voltage. Current also you can see that it is charging for more and discharging for less amount of time. And obviously like the peak current, right, Iomax will be this value. Why? Because at omega t equals to pi, this is my Iomax, right? At omega t equals to pi, we get like the maximum value of current. Why? Because after that the inductor discharges. After pi, omega inductor discharges. As it discharges, obviously the current will reduce. So just before pi, what is happening? Just before pi, my, okay, where did it go? Here, just before pi, this from alpha to pi analysis, IL is increasing, right? Inductor current is increasing. Just after pi, what is happening? This overall power is negative. That means inductor is supplying here. The voltage across the inductor is some negative value. That means what? That means my IL is reducing. Okay, because it is discharging. So obviously, just after pi it will reduce, and just before pi it will keep on increasing. So it will increase and up until this maximum value. At omega t equals to pi, then it will decrease to some other value. And at beta, the overall the current will become 0, and at alpha also the current will be 0. Okay, so these are the waveforms, current and voltage waveforms. So like one important point, key point that we must understand is that in a single phase half wave rectifier, right, it is impossible to achieve continuous load current if it is a single phase and half wave. That's why we don't use half wave, because it is very hectic. Even though in full wave we require more devices, I will explain that when we will study full wave, but we use that because there, right, we can easily achieve the continuous load current. Continuous load current means basically the current, right, current is flowing continuously in the circuit and the current never goes to 0. Okay, continuous conduction, like load current or continuous conduction. Okay, so here, right, what I can say is, if I reduce, like I will like assume few cases, if I reduce my fire angle, so if I trigger earlier, what will happen? The beta will increase. Why? Because obviously it will take more time to discharge. Why? Because it has charged for more amount of time. So the time, like it has more energy now. So that same energy, it has more energy because as alpha is lower, so the charging time increases. Charging time increases. Hence, it has more energy. If it has more energy, it can like dissipate more energy now. It has more time to dissipate that energy. Hence, beta will be increased because the time when the current will go to zero will be much later than this, as it has more energy now. The IO average will increase because more conduction period is there, that is beta minus alpha is the conduction period. VO average will also VO average, right? VO average will also increase. Why? Because if I write this expression, right, what is VO average? What is VO? VO is simply VR plus IO into, sorry, not VR, VR plus VL, right? VR plus VL. So what is this? This is IO into R plus IO into R plus VL. So if I take the average of both, this will be IO average into R. And did I tell you? Overall average throughout a cycle, right, of inductance voltage will be 0 volt second criteria. This I have explained in my previous lecture. So obviously it will be IO average into R of VO average, right? That is equal to my VO average. Hence, as IO average has increased and R will obviously be constant, so obviously VO average will also increase. Okay, VO average will also increase. So next, continuity of IO will also increase. Continuity of IO will also increase. So I'm just dividing it by case. What can happen? This can be asked in MSQs as well. So next, if inductance is increased, if the inductance is increased, what does that mean? That means that my beta, right? Beta will be increased. Why? Because inductor can store more energy. Why? Because what is the energy formula? Like this is not always the case that this is the energy formula, but like we can still get an intuition, right? Half Li square. And they have said that inductance is increased. So if inductance is increased, that means my energy is increased. If energy is increased, that means it will take more time to totally de-energize or totally make the current zero. It will take more discharging time. So obviously, if this increases, right, again the same thing, the IO average will increase because overall the current is non-zero for larger amount of time. So obviously this will happen and everything else will follow. VO average will increase. So this is just to explain you the few basic things about the parameters of the converter. If few parameters are changed, how will it affect the other parameters? So this basic intuition you should have. Okay, now let's come to the average output voltage. So VO average, right? VO average output voltage equal to 1 by T integration from like overall cycle, integration over a cycle, VO of T dt. So this is equals to 1 by 2 pi alpha to beta Vm sin omega t d omega t. Okay, so my average voltage I can integrate from alpha to pi, because after that what is happening, the voltage is 0 simply because the SHR is off and voltage output voltage is 0. So if I integrate this, right, I will get this equation. So this is very simple, just alpha to pi I am integrating, alpha to beta I am integrating, right? If you can integrate simple sin omega t. And what is my VO? VO is IO into R plus VL, and I just derived in the previous slide that my VO average will be equals to IO average into R. So my IO average will be VO average into R. So I will solve my VO average, and from there I will find my IO average. I will not remember a separate formula for IO average because this will also be formula for IO average, but we don't need to remember extra formulas. Just remember this. This is the basic thing that you don't need to remember, right? This is from intuition that you understand that my VO average will be equals to IO average into R. Why? Because the average inductance voltage throughout a cycle will be 0. And here, right, one thing to keep in mind, I'm assuming my expression is Vm sin omega t, because assumption is that my transient dies down, the right second term, right, of transient term that dies down. I'm talking about steady state. So this is the average voltage expression. Now what is the average current expression? So here, right, instead of going from alpha to pi, now we are going from alpha to beta. So if you can derive, I will write this after the end of the lecture, basically the derivation, but this is a homework, this is the assignment. Just derive this, right? Derive this from here to here. Okay, how do you come? But I will say that you don't need to remember, but if you want to, you can, because here, right, just instead of beta, if you replace it with pi, this will be the like formula in case of the first case, right? In the first case. So if you replace beta with pi, you will get the formula as such. Okay. No need to don't need to remember this too much, because this may not be that much important. If you want to remember, you can, but I will recommend, this is low priority, right? So not that important. Not very important. Because obviously they don't ask RMS voltages in questions. Okay. Next, analysis of load. So efficiency is what now here, right? They can ask two times, like in this. Okay, in this case battery is not this. So efficiency is like converter efficiency is what? Converter efficiency is simply PO DC by PU. Okay, PO DC by PU. And what is the DC power dissipated in the resistor? It is IO average whole square into R. So the DC component will be IO average whole square into R, and the AC component will, like AC plus DC component, overall component will be IO RMS into whole square by R. And I will just take the ratio of these two. So my converter efficiency will be simply IO average whole square divided by IO RMS whole square. Now what about the supply side? So in the supply side, right, my Vs will be Vm sin omega t. My RMS value of supply will be Vm by root 2. That this will never change. But my IS average, right, will be equals to simply IO average, because IS is equals to IO always. So this will be same as Vm by 2 pi R. Cos alpha minus cos beta. Okay, so you just numerically find out IO average from VO average, and from there you can easily write your IS average as well, because these two things are equal. Now what about the power factor? So power factor, right? Power factor, I can say that is equals to cos phi s equals to PS by SS. And if the converter is ideal, right, equal to supply power by apparent power of the supply. If the converter is ideal, that means my output power, and this will be the ratio of output power and apparent power of the supply. So I can further simplify this. What is my output power? It is IO RMS whole square into R, because my inductor is not absorbing or delivering any power throughout a cycle. Throughout a cycle, the average power becomes 0 for the inductor, right? So that I have derived in the previous lecture. And what is the SS? Basically the supply apparent power. It is VO RMS, so not VO, VS RMS into IS RMS, that is IO RMS. Right? IS RMS is IO RMS. So IO RMS will get cancelled. So this will be simply IO RMS into R divided by VS RMS. Okay. So like this I can further write this side. This will be IO RMS into R divided by Vm by root 2. Okay, by Vm by root 2. So this will be the answer. So like you can derive it. Generally they don't ask from these topics, but you should know, right? From basics you can derive always. You can always derive. Next is parameters of converter. Again, conduction period. What is the conduction period? It is simply alpha, beta minus alpha divided by omega. So this is the angle, and conduction angle is this gamma. So my conduction angle, right? If they ask you conduction angle gamma, it will be simply beta minus alpha, basically omega into T on. That is my conduction angle. The natural commutation time, it is the end period from beta to 2 pi. So 2 pi minus beta by omega will be the conduction natural commutation period. And again, this is a 2-quadrant converter, because this is delivering as well as supplying energy to the source, right? So now what we'll study about the RLE load. So we'll like do this bit quick, because we have understood the RL load. So we'll just write that in the equations, because just a battery is present, and the analysis won't change much. Okay, just hold on a second. I will drink a bit of water, then I can come back. Now let's analyze our half wave rectifier with simple RLE load. So like things won't be much change here. Just here one battery will be present, and due to that battery, right, the extension angle will change. Now it will depend if it is a generator or a motor. So what does a generator do? It supplies the energy, right? So this generator will also supply this inverter some energy. Okay, but if a motor is present, it will take some energy from the inverter. So due to that reason, if my generator is like conducting from alpha 1 to beta 1 and my motor is conducting from alpha 1 to beta 2, my general assumption will be that beta 2 will be more than beta 1, because during the first case, right? Okay, I wrote this wrong. Beta 1 will be higher than beta 2, because during the first case what will happen is that the generator is not absorbing any energy. Okay, it is also supplying energy to the inverter during the charging period. Okay, so inverter has more energy now, so it will the current will become zero at a later stage. And motor, right, during when it is charging, when it is energizing, the motor energizes from the supply, and the inverter also energizes from the supply when the period alpha to pi. From the period alpha to pi, the motor and the inverter both energize from supply, both take energy. Okay, so the energy that could have been taken by the inverter, that is being partially used by the battery. Okay, that is being partially used by the motor. That's why the inverter will have less energy in case of a DC motor. But when there is a generator here, the energy is not taken by the generator. Generator is also supplying some energy to this inverter, and supply is also source is also supplying some energy to this inverter. So inverter is getting more energy now. Hence, it will the current will become zero at a much later stage. That's why the conduction angle beta 1, extinction angle beta 1 will be very high than the beta 2. So this is just assumption. Okay, so but don't worry, we will just understand this motor case, and you just put you don't need to worry about this. Just put E equals to minus E for generator, and that's it. Everything will be sorted, because generator supplies doesn't take some energy, right? So don't have to worry about this. More about this when we will study during DC motor, when we will study in machines. So again, what will the control period here? So mainly I will assume that my E is positive. Okay, assumption is E is positive. You can do at homework for the case E is negative. Also, what you can do, the homework for you is simply analyze the RE circuit. I will analyze the toughest one, RLE, and you just make R0, and all the analysis will remain same. So you also analyze for the RE circuit. So here, right, first of all, I will decide what is my conduction, forward blocking mode. What is my forward blocking mode? I will assume what is my forward blocking mode, right? So again, my forward blocking mode will be different this time, because I have a E as well. So E will be somewhere around here, plus E. Okay, and this is Vs. Now why am I drawing this E? We have analyzed simple RE load. Now we understand why do we write E here over here. So if you want to compute the VT now, what you will see is VT is simply equals to Vs minus E. Why? Because I have explained in my RE load that VL is 0. Okay, because IL 0 minus is 0. My VR will be 0 because IO is 0, right? IO 0 minus is 0, IL 0 minus is 0. Hence, what is left? What is VO equals to? VO is equals to simply VE, right? VO is simply equals to E. So basically, my left and right, the anode voltage is what? Vs, and the cathode voltage is E. So my threshold voltage will be Vs minus E this time. So obviously, the region of forward blocking mode has reduced now, because E is positive. That is my assumption, right? So the region of forward blocking mode will be only this. Region of forward blocking mode will be only this. Okay, so this is my region of forward blocking mode. And what is the region of reverse blocking mode? Region of reverse blocking mode has increased from here to here. So again, what is this angle called? This will increase from here to here, because here also it will still be in reverse blocking mode. If I observe it carefully, this will become more, but at this point, after this point, the overall voltage becomes positive. Before this, the overall voltage is negative only. So this will be my reverse blocking region, the region of reverse blocking. Okay, and what is this angle? We have some name for this angle, right? This angle is what? This angle is theta, and this angle is pi minus theta, and this is 2 pi plus theta. Okay, yeah, that's the only thing. And yeah, these are the important points, right? Here my VT is either greater than 0 or less than 0. So this time, right, my alpha minimum is what? Alpha minimum, right? Alpha minimum will go from theta to pi minus theta. That is my range of triggering angle. So my alpha minimum will go from theta to pi minus theta. So this is my alpha minimum, right? This is my alpha minimum, and like if you replace it with this alpha minimum, this will be converted into diode circuit, simple diode, right? Not controlled anymore. So obviously the range has reduced for forward blocking mode. So what will happen? Just the cases will change now, except that everything will remain same. So in the case one, why I'm starting from theta to alpha, I will explain you just in a minute when we finish it. So from theta to alpha, what my assumption is, obviously it is in the forward blocking mode. So if it is in the forward blocking mode, I haven't triggered my SCR yet, because at alpha I will trigger. So everything is 0, right? If everything is 0, that means my IS is 0, like IS is equals to IO equals to IT equals to 0 amperes. Okay, hence my everything is 0, hence my VO is what? VO is simply E, right? Because VL is 0, VO is VL plus VR plus E, and VL is 0. As VL is 0, VR is again 0, because IO is 0, right? Hence it will be simply equals to E. VO will be simply equals to E. Okay, and my VT, again VT is simply VS minus E, and I know, right, VS is less than E. In this region, VS is less than E, so obviously it will be less than 0, hence SCR is in the reverse, not reverse, sorry. Okay, sorry, no, I'm sorry, I told you wrong. I'm starting from here, right? I'm starting from this theta, so obviously VS will be higher than E. So VS is higher than E, and I haven't triggered the SCR, but SCR will be in forward blocking mode because it is positive. It is positive. The thyristor voltage is positive. Okay, so hence SCR will be in forward blocking mode. Now let's come to the case 2. In the case 2, I have triggered at omega t equals to alpha, SCR is triggered. So if SCR is triggered, SCR will close. Okay, now what is happening? Like I will not too much analyze this, because I have already analyzed the RL circuit. I will analyze this in a fast manner. So SCR will be in forward conduction mode. So if SCR is in forward conduction mode, that means what? That means my VT is 0 volts, VT is 0 volts, my VO is directly equals to VS. And what about my VL? So initially, right, just initially, my VL of 0 plus will be what? Simply equals to VS minus E, right? VS minus E, because like this is 0, right? This is 0, and this drop is 0, because I will assume that, oh not, sorry, this is not 0 plus, actually this is alpha plus, because I'm triggering it alpha. So I will write this more precisely. This will be alpha by omega plus. Alpha by omega plus. Okay, alpha by omega plus. Now what about this? What about this? Basically my inductor voltage is positive, that is my DIL by dt is positive. That means my IL will increase. Okay, so slowly IL will increase. That means my inductor is energizing. And what is the direction of power flow? Direction of power flow is simply from source to load. Why? Because IS can also only be positive, and VS is already positive, right? VS is already greater than 0. VS is already greater than 0, and IS can only be greater than 0, can never be less than 0. Okay, hence my power PS supply, right, will be greater than 0. It will not absorb, it will deliver power, right? So all these things are there. Now at what angle will the SCR close? At pi minus theta, right? This time pi minus theta is the important angle over here. At pi minus theta, will the SCR will the SCR turn off, or at pi will it turn off? So at pi minus theta, if I observe one thing, at pi minus theta, my SCR voltage is my supply voltage is what? Still greater than 0, right? Supply voltage is still greater than 0. Okay, that is one thing. But what can I say is VS is equals to E that time. VS is equals to E. VS minus E equals to 0. Okay. What will happen is that supply voltage is E, and what is my VL? What is my VL? So my VO, right? VO is equals to VS equals to simply IO into R plus VL plus E. Okay. And what do I know? I know at theta, right? At pi minus theta, Vs is equals to. So I can replace this with E. So what will be my VL? What will be my VL? So VL will be simply minus IO into R. Okay. So VL will be simply minus IO into R. So what does this means? This means that my, like this IO, right? IO can only be greater than or equals to 0. IO can only be greater than or equals to 0. And what can I say here? What can I say? So my VL from this I can deduce that VL is less than 0. That means VL is discharging. So here the current will obviously be reducing, right? Because IL will obviously, like, or IL or IO will obviously reduce. And what more important point is that, will the source still supply the power? Will the source? No, right? Why? Because like from this point on, the inductor is discharging. Basically from this point on, right? From this point on, what can I say? I can say that the power flow, right? Power flow, if I just draw the power flow diagram, power flow is happening from the inductor, okay, to what? To the R and the E, right? R and the E, okay. And obviously the supply is there as well, right? Vs supply is there as well, because overall what did I say? I said that this IS is positive. Okay, one thing is important. IS is positive. Just hold on. IS is positive. IS is positive, and this Vs is also positive. Okay, this is giving some power. So one important point here is that this is giving some power, and inductor is also giving some energy. Why? Because VL is negative, right? I know VL is negative. VL is negative. So inductor is also giving some power because IO is still positive. So VL into IO is negative. That means inductor is giving some power. To whom it is giving some power? It is giving some power to resistor and the battery, right? It is giving some power to resistor and battery. That means what? That means that it is not giving power to supply right now. So it will discharge. What I will say is, I will say here itself that it will discharge, but it will not discharge super fast. Why? Because it is not giving energy to the supply right now. It is giving energy to the resistor and the battery, right? It is giving energy to the resistor and the battery. So what I can say is discharging slowly. Okay. Now one case one case I should have written over here. I missed one case, so I'll just copy and paste, and then I will say you what case am I talking about. What case am I talking about? So computing the value will be very difficult for us, so I will not talk about that. So this value, right? This value will be, just hold on, let me check if everything is fine. So here, right, let me mark this angle as any angle. Let's say theta, gamma, beta, alpha, sigma also we can do. Sigma is used. Gamma is also used. Any angle, right? Let's say that angle is, I'm just getting out of angle names right now. So that angle is theta x, okay? Theta c, let's say theta c. That angle is theta c. Now theta c, what is happening? I'm assuming that my VL goes to 0. Why my VL goes to 0? Why my VL goes to 0? Okay, why? Because what you will see is that if my VL goes to 0, that means what? That means my VL is equals to what? VL is equals to Vs minus IO into R minus E. Okay, so even though this is positive, right? This is positive, but this can still be negative, right? Like, sorry, this can be equal to what do I mean by this? That my VL is 0. I'm assuming my VL is 0. So what is happening? My IO into R is equals to just hold on, is equals to Vs minus E. My IO into R is equals to Vs minus E. Now what will happen here is, as my VL is 0, and after this, what if my, let's say, IO like Vs is increasing, right? If my Vs is increasing, so Vs minus E, this will increase, hence the IO will try to increase, right? Hence the IO will try to increase. But like from this angle, right, what I'm assuming is that Vs is not increasing, Vs is decreasing. So I'm lying in this region. I'm lying in this region, let's say. Here, right, Vs doesn't increase, Vs only reduces. So if Vs reduces, if Vs reduces, I into R will reduce. Why? Because I have assumed that my VL is equals to this. Okay, VL is equals to this. So what is happening over here is that as my Vs reduces, overall this VL will reduce, overall this VL will only reduce after this. So VL is only reducing. So if VL is reducing from 0, what will happen? It will become something negative. That means that my inductor is supplying some power. Inductor is supplying some power to the load again. To which load? To the resistor. Okay. Not to anything else, only to the resistor. Okay. This is my inductor and this is my power flow. Okay. So inductor has to supply to the resistor now. That means it is discharging now. That means from this point only, from this theta C only, the IL will keep on reducing. IL will keep on reducing because after this what is happening? Like inductor will start to supply, right? It will first supply the R, then it will supply the RE, then it will supply finally the VS. So there will be this type of cases. So this is very interesting to know. Please do keep this in mind. So here what will happen? What can this theta C maximum be? Theta C maximum can be pi minus theta. Why? Because if there is no resistor, right, it will start to give energy to the battery only at this pi minus theta angle, because then only this VL will be negative, because I into R won't be present, and if R is 0, then this VL is 0 at this particular theta, right? At this particular omega t, VL is 0. So from there also you can understand this intuitively, right? So it will discharge again, discharge, but slowly, more slowly, right? More slowly. Next case, it will discharge in a fast manner, but still slower. Why? I will like explain in the last case, right? So this case, let's say this is the 3, I will name this as 3A case, okay, and this is a 3B case. So in case 4 is what is happening? Case 4, right? Like inductor will not try to change its state, so still current will be some positive value. And inductor, I will take this example, the current hasn't reduced to 0. So current will be some positive value. If current is some positive value, right? If current is some positive value, and after pi, right, my Vs is equals to less than 0, right? Vs is lower than 0 because Vs is reducing, and my Vo is equals to Vs. So obviously I can safely say that power, right, this time the inductor will supply everyone the power, okay? Like inductor, here I have L, that is the load, that will supply power to everyone now. R, the supply as well, because this Is is positive but this Vs is negative, so Vs into Is product becomes negative, hence, and obviously the battery, okay, it will supply the battery as well. So flow of power is going to 3. So here, right, this will discharge the fastest, like de-energize. I should not say discharging, I should say de-energizing, right? De-energize the here slowly, and at the last, this third case, right, it will de-energize fast, okay? So these are the things actually about this case. So like, why is it de-energizing the fastest? You can understand from this as well that what is my VL now? Can write down my VL is equals to what? Vs minus IO into R minus E. So this time IO is obviously positive, this is getting subtracted, this is getting subtracted, and this is also negative. This is also negative, right? So everything is negative. Everything is negative. Okay. Hence my VL will be very low, very low. Okay, very low, lower than 0. So this will discharge faster here. So this will this will de-energize slower here. Okay. So these are the different regions of energizing and de-energizing, right? So next, like at beta, we will assume that obviously the current has gone to 0, so SCR is off, and then again this will repeat, right? Basically my IT equals to IO equals to IS equals to 0 amperes. Okay, and my VO equals to simply E. Okay, in this region my VO is equals to simply E, and my VT is equals to Vs minus E, which is obviously less than 0 because I'm lying in this region, right? I'm lying in this region. Okay, this will be always, Vs will be always lower than E, hence Vt will be negative, hence I will be in the reverse blocking mode. And what has happened? Natural commutation has happened, right? Natural commutation has happened. Okay, so alright, this is LC, NC will mean something else. Natural commutation. So these are the equations, basically these are the equations. So if when the SCR is on, right, so we do this by superposition. We first assume the current due to the sinusoid response source, and then the current due to the battery. So current due to the battery will always be E by R. Okay, if I apply superposition, and when the SCR is on, current due to the battery will be E by R in the negative direction, because E by R current will flow like this. Okay, but obviously actually through the SCR that current is not flowing, right? Overall current will be positive only, but just for superposition we are using superposition here. Okay, so this part we already know, but this was the extra part, just E by R extra current, that will obviously help in turning off the SCR even before than omega t equals to pi. That's why this E by R is trying to reduce the overall current. So this will make the current 0 at a much faster rate, right? So this is IO into T, this is phi Z, all those things, right? This we already know. Again, if you put omega t equals to alpha at omega t equals to alpha, what condition we know? We know our I of t will be equals to 0, sorry, not 0, and from there you will be able to find the value of A, right? Like if you want to find the value of unknown A, from there you will be able to find value of A. And another case is how to find the extinction angle at omega t equals to beta. At omega t equals to beta, what do I know? I know my IO of t again will go to 0. My IO of t will again go to 0. Okay, hence what will happen? Again you have to solve using numerical methods. Solve using numerical methods. Okay, solve using numerical methods. So these are the things that you need to keep in mind for RLE load. Now here, right, in the graph there will be a bit difference because I have done a bit thing wrong here. So this pi minus theta, right, this pi minus theta will be somewhere around here, will become somewhere later. Okay, this value is E only, so okay, this is VO only, right? So at VO, like VO will be 0 when VO will be 0, like VO is equals to what? VL minus VO is equals to VS always. VO is equals to VS, so this value will be this only. Pi minus theta will come at the right hand side. Why I will explain. Okay, no, here pi minus theta will be same here, but in this region. So this waveforms I hope we understood. Like VO when it is off, right? VO when it is off, it will always be equals to E. This value is E, right? Because there is no drop across the resistor, hence the whole battery voltage comes across the output. So whenever the SCR is off, it is E, and whenever the SCR is on, it is simply equals to VS. It will follow the input. So plotting the VO is very simple. Okay, and SCR voltage, whenever SCR is off, it will follow the input. Okay, and like one thing you have taken care of is that, okay, I like messed up one thing. This value, right? Obviously I have to subtract by E also, because this time a battery is present, so this value will be Vm sin beta minus E. Okay, so this will be few things, yeah, except that everything will be same because I have to subtract by E, right? E is present over here. So on the right and the cathode side, the SCR voltage is E, and theta is sin inverse E by Vm. Okay, and this is with RLE load. All the waveforms are with RLE load. Now for the current waveform, here I have done a bit of mistake. Here I have told that at pi minus theta, the current will reduce, but the current will actually reduce a bit before that. So if I just shift this on the right hand side, if I shift this on the right hand side and I mark another point, let's say this point, this is the maximum point, right? So let's mark this point as theta c. I've explained this theta c, right? Here what is happening, current after this theta c is reducing, not at this point. Why? Because from here, right, it is like delivering some energy to the resistor, then after this point this is delivering some energy to the resistor and the battery, and from this point, right, from this pi, it is delivering some energy to the both the resistor, battery, and as well as the source. So I will write this in this region. So from here, right, I will write this here I will write, okay, Iomax will not be omega t minus phi, it will be simply, the difference will be, Iomax will be simply theta c minus phi. Okay, Iomax will be theta c minus phi, not pi minus, because this is the maximum. Like, what is the current expression? Expression is this, obviously minus, like, don't forget I use a superposition, so minus e by r is also present over there. Okay, minus e by r is also present, right? So these are the max, and like I will write down few things, jot down few things here. So how can I jot down? That is what I am trying to understand. So okay, I don't have enough space. So here, right, I will summarize quickly these things. That from theta, like we will say from alpha to theta c, what is happening? IL is increasing, right? IL is increasing. Hence my inductor is energizing. Then from theta c to pi minus theta, what can I say? My IL will reduce. Why? Because inductor is de-energizing through the resistor R. Okay, through the resistor R. From pi minus theta to pi, IL will reduce very faster, much faster. Okay, as it is de-energizing through R and E. Then from pi to 2 pi plus theta, right? Not 2 pi plus theta, pi to beta. I will just okay, this dash may seem a bit misleading. From pi to this, right? This arrow might be better option for us. So from pi, not sorry, okay, yeah, this is pi minus theta. Actually, that's got misleaded by me as well. So this is the arrow, right? This is the arrow. And from pi to beta, like current is still positive, it is de-energizing at a much faster rate. So this will be 3 arrows on the downside, and here, right, this will de-energize through the battery, it's not through the source as well. So obviously I can see, like, it will like discharge time will always be less than the charge time, and it will be even lower this time. Okay, so discharge time will be less than the charge time. So yeah, here, although like pictorially this is you're not able to understand, but still you should understand this, that discharge time, right, will be, because it will discharge at a much faster rate now. It will discharge at a much faster rate. So we'll just reduce this thing. Okay, change this beta here, just changing few things to make everything aligned, right? So yeah, this so beta will again reduce, 2 pi plus beta will be somewhere around here. Okay, this will be VL. And again, right, this point has zero, so the inductor voltage will not go, should go negative somewhere around here, which is correct. So wherever this inductor voltage goes negative, right, that is the actual point of interest for us. So I will just copy this, duplicate this, and paste this over here. Wherever this inductor voltage goes to 0, okay, that is my point of interest, because after that the inductor will only discharge. Okay, after that inductor will only discharge. So this 3 pi minus 3, right, can be shifted on the right hand side a bit, and I can again duplicate this. This will be somewhere present on here where the inductor voltage exactly goes to 0. That is my theta c point. Okay, 2 pi plus theta c, actually this time it will become 2 pi plus theta c. Okay, so yeah, these are the things. So here I will say that charging time will always be greater than discharging time. Okay, charge by charge, it means it is getting charged by flux only. Okay, so this will be the most corrected waveform. Trust me, no one will draw the waveforms like this, and like I have seen other educators also teach, so they never draw the waveforms correctly. There is some mistake or something else. So if you understand this conceptually, you will always draw this correct. So like, let's now go into the parameters of the single phase rectifier, right? So here I have average output voltage. So VO average is equals to this, and from alpha to beta, and obviously there is this factor as well, right? E from beta to 2 pi plus alpha, because whenever this SCR is off, right, then my output voltage is E, hence the overall output voltage actually increases, which like increases the efficiency. So VO average will be this formula. So don't need to remember this, you can always derive, right? You can always, or you remember this, just add E into 2 pi plus alpha beta with this, and that's it, right? And what will be your IO average? So your IO average will be like VO will be equals to IO into R plus VL into E, and if I totally take the average on both sides, right, obviously my VO average will be equals to IO average into R plus VL average, which is 0 due to the volt second criteria, and E average of a constant number is that number itself, E. So overall IO average will be equals to VO average minus E by R. Okay, and like, what are the efficiency? Efficiency is this, right? Efficiency of the converter is simply PO DC by PO. So now what is the DC power dissipated? DC power is IO average whole square into R plus EO into IO average. Only this is the DC component, and the RMS component is this. Okay, overall power. Now what can they ask is, they can ask as like efficiency like this as well. That is the battery charging efficiency. Battery charging efficiency. What will be that? That will be simply equals to what? That will be simply P like EO into IO average, because I am just computing the power I got due to the charging of the battery, not like the power that has been dissipated in the resistor. That is not much useful to us. So EO into IO average divided by overall power, that is IO RMS whole square into R. So that is already been derived here, so I won't change that. That will be same only. That will be same only, but this has been changed, right? This has been changed. So these are the things. So like this and this has this different, that I explained that as well. Okay, because there is much confusion between this and this, so I've explained the two things. Now supply voltage will be same only, and it will like RMS will be VM by root 2, and IS will be IO like IS average will be IO average. And don't worry, you don't need to remember RMS. Okay, IS RMS is not needed. Okay, not needed. Why? We'll understand when we will study about the constant load. Okay, constant load. So then your supply analysis, like your power factor will be PS upon SS, and if the converter is ideal, ideal converter. Okay, if the converter is ideal, then obviously PO will be equals to PS. Okay, so these are the things. This you basically know. And what is PO? PO is basically IO RMS. This will be given to you, don't worry. IO RMS will be given to you, R plus E into IO average divided by VS RMS into IS RMS. Okay, so this will be the power factor. This is how you compute the power factor for this particular rectifier. Now what is the conduction period? Conduction period, right? Conduction period is simply from beta minus alpha by omega. These things will remain same because everything is same, just that there is a battery. Due to that, the like beta will reduce. Due to that, beta will reduce, right? So peak inverse voltage. Now this thing you should know. What is the peak inverse voltage? Peak inverse voltage will be the voltage in the negative direction when the SCR is still on. Maximum reverse voltage that it has to block. What is the maximum reverse voltage? So SCR is on till beta, right? SCR is on till beta. So here beta, right? I can observe that at beta, it has to block the maximum reverse voltage. After that, it will only reduce. So this peak inverse voltage, it also will depend on the value of beta. So here, if the value of beta is lower than 3 pi by 2, if the value of beta is lower than 3 pi by 2, okay, this will be equals to this. If value of beta not lower, sorry, is greater than 3 pi by 2. So I will just reduce this. Let's keep this on the side. So if the value of beta is here, in this case, this will be equals to this. If value of beta is greater than 3 pi by 4, not 4, 3 pi by 2, and is obviously lower than 2 pi. Beta has to be lower than 2 pi, obviously. So this will be the second case. And if my beta is lower than 3 pi by 2, then my peak inverse voltage will be Vm plus E. Am I correct? Minus Vm, and it is also minus E. Sorry, Vm minus E. It will be Vm minus E, not plus Vm minus E. Why am I writing this? So in this region, it is like my beta is between beta has to be lower than 3 pi by 2 and it has to be greater than pi. Okay, so here what is happening is that if let's say my SCR is turned off before this here, okay, before it reaches minus Vm. So if my SCR is turned off before this 3 pi by 2, what will happen is that the voltage, right, this voltage will cross through this minus Vm and then reduce, then go towards 0. But if my SCR is turned off in this region, right, so what is the maximum negative voltage that will come across the anode? The maximum negative voltage will be something that is lower than Vm. Okay, that will be equals to what? Vm sine beta. That is the maximum negative voltage that will come across the anode. Okay, so after that it will only reduce. So what is the maximum negative voltage that can come across the anode? That is my Vm sine beta. Okay, Vm sine beta. So these are the things that we need to understand. So if my beta, let's say, was here, right, it extinguished before this 3 pi by 2, so voltage here is still going more negative, and it will go negative till minus Vm. That's why if my beta is lying between this region, right, 3 pi by 2 to pi, then the maximum reverse voltage that will be applied across the SCR will be minus Vm. Then after 3 pi by 2, if my SCR is turned off in this region, right, then the maximum negative voltage will be equals to the minus Vm sine beta, obviously, and minus E obviously is there, that is constant. But you have to understand the maximum peak voltage, the maximum negative peak voltage across the anode will be only Vm sine beta, and that will be automatically negative. And after that it will increase towards 0. It will go towards 0. Okay, it will not reduce. Okay, that's why I have two cases for peak inverse. So if they ask if somebody gate frames a good question, right, they will frame a good question from here, and everyone will make it incorrect. Okay, one student will be confused with this solution, one student will be confused with this solution, and both will be in the options, trust me, and they will get confused. So you have to understand this as well. What is the peak inverse voltage, all those things, right? So this way gate can trick you. So now we will solve few questions. So what I will do is quickly I will pause the video and I will like show you these questions, and you can pause the video and try it for yourself. Then I will solve all these questions. This is 12th one, this is the 13th one, this is the 14th one, and this is the 15th one, right? So all these 15 and 16, all these questions you solve, and I will come back and then solve in front of you. Okay, let's solve this first question, that is the 12th one. Okay, so this is like a simple RLE load, and we have an inductor here. So whatever we have learned, right, all those knowledge we'll use for solving this question. All those knowledge will apply. So first of all, here we have a simple RLE load, and value of R, E and L are given. Okay, although this value of L, right, it is irrelevant, we don't need to check. But like, because generally what will happen is L will be very, very high and the time constant of the circuit will be very, very low with respect to the time period. Okay, if you didn't understand what do you meant by this, so obviously you have to watch transients from PrepFusion. Okay, so here, right, first of all, they have given us this guys here, and they have given us the triggering angle alpha is 25 degrees and beta is 220 degrees. Okay, and our supply is RMS is 230 volts and 50 hertz. What are they asking? They are asking us the value of Vt just before the instant SCR is triggered and at omega t equals to beta, that is at the extension angle. What is the value of my thyristor voltage just before and just after it? Or I can say just at omega t equals to beta is also fine. So just before it, right, obviously I know alpha first of all, like we should do a quick sanity check. Alpha must be greater than theta, right? What is theta? Theta is simply E by Vm sine inverse E by Vm. Theta is sine inverse E by Vm, right? So obviously we need to check this, right? We need to check the value of theta. So like obviously we don't need to check, like for gate question you don't need to check. With generally what will happen, your alpha will be greater than theta, and obviously your SCR needs to be in forward blocking mode, then only you can trigger this here, right? Else you cannot obviously trigger this here, SCR will not turn on. But still, like as we have more time, we will check all these things here. So what is my E? E is 120 volts, right? E is 120 volts. And what is my VM? VM, right, is not 230. You'll not make that mistake. VM is 230 root 2. 230 root 2 because VRMS is 230, right? So now if I compute this, right, what is this? What is this? This is 120 divided by 230 into 2 under root, and if I take the sine inverse, right, sine inverse is 21.649 degrees. So theta is 21.649 degrees, and which is correct, right? My alpha is greater than this. What is alpha? Alpha is 25 degrees. So fine, my SCR will be in forward blocking mode. Just as a quick sanity check, I done this. Like in the examination, you don't need to do all this. This will be anyways fulfilled. As the question will be not that the question will be wrong. The question will become very tricky then. Okay, question will become very tricky then. Then there is no meaning to triggering the SCR, right? SCR will never turn on. SCR will never turn on. Okay. So there won't be any extinction angle because question will be wrong because SCR is always off. SCR will be always off. So now we need to find out Vt. What is Vt? Vt is simply Vs minus Vo. And I know, right, just before triggering SCR is off. If SCR is off, my Vs is like my Vt is Vs minus E. Because why? Because my IO is simply 0, right? IO is simply 0 amperes. So what is Vs? Vs at that point is what? It is Vm sine alpha, right? Minus E is 120. Okay, E is 120 and Vm is 230 root 2. So I'll just compute this real quick. Okay, so basically 230 times root 2 times alpha is 25, sine of 25 subtracted by 120. So it must be some positive angle, and exactly that is what we get. We get 17.465 volts, which should be right. It is in forward blocking mode, so it should be positive. It should be in positive, right? So this was the first part, and the second part is what? Second part is at omega t. So at omega t, right, again the current will be 0. So at omega t equals to beta. At omega t equals to beta, the current IO will be again 0 because that is a definition of extinction angle, right? The current extincts at that particular angle. So what will be the voltage across the thyristor just after it? Just after beta, because the current will be off. So like here, right, this also will be open circuit, and here also this also will be open circuit, and the current IO will be 0. Here also current IO will be simply 0. So same thing again, my VT equals to Vs minus E. Okay, so Vs is what? Vs is Vm sin alpha minus E. What is E? E is 120 volts. Okay, again I will apply the same thing, not alpha, sorry, sin beta, right? Omega t equals to beta. Beta is beta is 220 degrees, right? Beta is 220 degrees. So if I just write down the beta will be 220 degrees. So 220 sine of 220 into Vm is 230 into root 2 minus 120. Okay, so this will be almost minus 329 volts. Okay, this will be minus 329 volts. This will be the thyristor voltage at omega t equals to beta. So these are the answers. One is 17.465, another one is minus 329 volts. Just after the instant the thyristor gets turned off. So now let's come to the next question. So in the next question, again a RLE circuit is given. We have to determine the battery charging current for the given below circuit, where R and E values are given, supply is given, alpha, beta, everything is given. Now what do I mean by battery charging current? What do I mean by battery charging current? Battery charging current, because like battery charges only through DC current, right? DC current. So here, right, my battery charging current will be IO, will be IO average. Basically the current that they are asking, charging current means DC current, IO average, because this is the current that they are asking. Okay, so how do I find out IO average? So what I will do, first of all I will find out VO average, and from there I will find out IO average. Okay, that is exactly what I will do. So here, like obviously you can derive the VO average formula, simple integration of Vm sin omega t from alpha to beta plus E from beta to 2 pi plus alpha, because whenever the series of the voltage is E, so that's why, and divide by 2 pi. That's how you compute the VO average, and from there you derive the formula. So you can derive the formula, that will take you 20 seconds to 30 seconds. That's fine. If you don't want to remember this, that's totally fine. I also don't want to remember this, right? Because I have other things to remember. So I will derive this at the examination hall, but just be good with the derivations and practice more this, right? Don't directly try this on the examination hall. Don't directly try to derive on the examination hall. Don't try any new things on the examination hall. Whatever you learned through practicing question, through the test series, those things you only apply in the examination hall. Don't try anything out of the world. Okay, 1-2 things you can try out of the world, but not like everything, right? Not everything. So yeah, that's how you should go along in the examination. So VO average is this formula. I know my Vm is what? Vm is 230 root 2 divided by 2 pi into cos alpha. Cos alpha is cos 60, right? Cos 60 plus cos 240 plus E. E is what? E is 100 volts. 100 divided by 2 pi also, because 2 pi will be divided with everything, into 2 pi. Now here, right, this is in radians. So this thing should also be in radians. So what is 60 degrees? 60 minus 240. What is this in radians? This is pi by 180. So overall this becomes totally minus pi. So this will be pi times this, right? Pi will get cancelled, and this will be only 50. Okay, this will be only 50. And what about this? 60 minus 2 pi, yeah, 2 pi minus all these things, fine. Yeah, this will be only 50. Am I doing this correct? Wait, one thing here is one thing wrong. Okay, this should be beta minus alpha or alpha minus beta. Wait a second. This should be, okay, beta by beta to 2 pi plus alpha. Yeah, 2 pi plus alpha minus beta. So yeah, 2 pi plus alpha minus beta. This is correct only. Yeah, this is correct only. Fine. 2 pi plus alpha minus beta. Fine. So this will be pi only. So pi will get cancelled, and here only a 50 will remain. Everything is correct. Plus this. What is this value? This value is 230 into root 2 and into cos 60. What is cos 60? Cos 60 is 0.5, and cos 240. Basically here, right, I have a minus. So minus will get plus here. So 240 cos, this will be plus, then I will close the bracket. Then obviously I have to divide by 2 pi as well, right? I have to divide by 2 pi as well. So if I divide by 2 pi, this will become 51.77. Okay, so what will be my answer if I just add these two values? This is my VO average. If I add 50 with it, it will be 101.774. So this is my average value. This is my average value of the output voltage. Now what is my IO average? So don't need to remember too many formulas. IO average you can easily derive from VO average, right? VO average minus E by R. Why is it the case? Because I know my VO equals to IO into R plus E plus VL for a RLE circuit. Now if I take the average on both sides, this will become VO average equals to IO average into R plus E plus 0, because VL average will be 0 due to the volt second criteria. So overall my IO average will become VO average minus E divided by R. Okay, divided by R. So what is VO average? VO average is basically 101.77 and E is 100. So current, actually charging current will be very low. E is 100. Okay, and divide by R. R is how much? R is 2, I think. R is 10. So if I subtract 100 with it and then I divide by 10, this becomes like the current value is very, very small. This is 0.177 amperes. Okay, so this will be my charging current, right? This will be my charging current. IO average. Okay, this will be the answer. So this is the next question. Next question is also very interesting here, right? This is a EL load, right? EL load. R is not present. EL load. So here we have to draw the inductor voltage waveform for the given VLSI circuit. So beta is this. So not beta. They have given the alpha and they haven't provided us with the beta. Okay. Now okay, beta also has been provided. That is 240 degrees. So beta I can write side by side. 240 degrees. Okay. So this is the supply, this is the LE load, and like alpha beta they have given. So how would the output voltage be? Whenever the SCR is on, output voltage will just follow the input voltage. So you have to plot the, okay, we have to plot the inductor voltage waveform. That will be interesting for plotting the inductor voltage waveform, right? What will be my inductor voltage waveform? So if I want to plot my inductor voltage, my VO is what? VO is VL plus E, okay, and my VL is VO minus E. So what do I know? I know that my, whenever this SCR is on, right, whenever this SCR is turned on, my VO will be simply VS. Okay, so whenever this SCR is on, VO will be simply VS, and whenever this SCR is off, that means what? It has settled. Current through it is constant, that is 0. So DIL by dt will be 0. So VL will be 0. Okay, so I can say this is SCR on, this is SCR off. Okay, so here the inductor voltage whenever SCR is on, VO will be equals to VS, so VL will be equals simply VS minus E, and whenever SCR is off, that means the current through the inductor is constant, 0. So DIL by dt will also be 0, hence VL will be simply 0, because VL is equals to DIL by dt. So like that I can understand, or like how, with what reference I should plot. So I'll plot with reference to the voltage, okay, output voltage. So let's say we have until this is 0 omega t and this is alpha, right? Up until alpha the inductor is, like the SCR is off. Then obviously suddenly what happens is that it starts to follow the input, because I triggered the SCR at alpha. So the output voltage starts to follow the input. and the voltage will be something like this. Okay, just hold on, it will follow the input. Obviously it can never go below E. Okay, it can never go it can go below E. Okay, I was just making this mistake. It will follow, because why will it go below E? Because the inductor will let it happen. Because inductor will still keep the SCR on even after pi. Inductor will still keep the SCR on. Okay, and then suddenly this drawing won't be perfect that much, but still just bear with me. Suddenly what will happen is that angle beta will come, right? Angle beta will come. Beta, here they have given us 240 degrees. So I'm just drawing this what do you say, without the exact variable, global names I'm drawing. So this is the angle beta, where what happens? The SCR turns off. If the SCR turns off, what will happen? The output voltage will be simply equals to E. Whenever SCR is off, the output voltage always is equals to E. So here in this regions, in this particular region, SCR of, this is the value of E, right? This is the value of E. Here in this region, SCR on. This region also SCR on, right? This whole region is SCR on, as output follows the input voltage basically. And in this region SCR is off until what? Until again 2 pi plus alpha. Again we'll come back to 2 pi plus alpha. 2 pi plus SCR will be off. Okay, so this will be 2 pi plus alpha and this. So one important thing to note over here is this is what value. So this value, right? This value is simply what? This value is pi, because at pi only the voltage, output voltage goes to negative. Okay, so these are the things here. And how will my inductor voltage be? So whenever SCR is off, right, inductor voltage is simply 0, because it has settled. It has reached steady state, so it will simply be 0. Okay, then what will happen is that it will suddenly match the supply voltage to make the current across the resistor almost equal to 0. Okay, almost equal to 0. So that's what it will match according to, like, it will match the supply voltage plus the this E, right? That's what it will match. Basically Vs minus E. VL will be Vs minus E just when it is triggered. Just when it is triggered, it will be Vs minus E. That is with this value, right? This value, I will exactly say you the expression for this value. This is what? This is simply Vs sin alpha minus E. Okay, this value is simply Vs sin alpha minus E, because at alpha, not Vs, sorry, Vm, alpha, the SCR is getting triggered. And after this, what will happen is that the inductor will be some non-linear function. I don't know exactly what this will be, but this will not be sinusoidal. This will be some non-linear function. So here, right, this will be some non-linear function. I don't know. So this, I exactly don't know what this is. This is definitely not sinusoidal. This is definitely not sinusoidal. Okay. Then what will happen is just some value before, like what value will be this? This value, right? This value will be pi minus theta. Pi minus theta. Because at pi minus theta, what will happen is that the voltage will go negative. Why? Because inductor will discharge after that. Because the this, right, what will be my VL at pi minus theta? What will my VL at pi minus theta? It will be simply 0, because Vs is equals to E and VL is equals to what? VL is equals to Vs minus E. Vs is equals to E at pi minus theta. That is proof, right? So VL will be 0. VL will be 0 and then it will go to negative. Why it will go to negative? Because it has to continue the flow of current and it will discharge through the, de-energize through the battery and the supply. So not the supply, sorry, through the battery, and after this pi, right, both through the battery and the supply. Okay, so I hope that thing got cleared. So it will be some negative value. okay, and it will go to 0 here, and this will be some non-linear function. This is so I am emphasizing on this that this is not sinusoidal, not sinusoidal, okay. And in this, right, this is the, let's say this is some value pi, okay, this is the value pi. So in this region my inductor is de-energizing through the battery, right, through E, okay. And here in this region it is de-energizing through the supply Vs and E both, okay, through Vs and E. So, and in this particular region it is energizing, because Vs and like Is is always positive and VL is also positive, so it is energizing. Okay, flux is increasing here. Here flux is increasing. Here flux is going to a 0. Okay, so this was the thing here, and yeah, this is the divisions. I hope you understood all this point. And here beta, right? At beta, the voltage goes to 0, and it will remain 0 till what? Let me just. Two pi plus alpha. Okay, 2 pi plus alpha. And one important, even this is not sinusoidal, this is some non-linear, right? This is some non-linear function. But what I can definitely say is that if this area is A1, okay, and if this area is A2, I can definitely say that A1 will be equals to A2. Why? Because my overall inductor voltage, that is VL average will be simply 0 volts. Okay, so this is the important point, and this is the plot. So this type of question can be asked, like graphically they can ask all these questions, right? So let's solve this next question. So there are two questions which are mainly theoretical here. Okay, so for a single phase half wave rectifier, just hold on, I will check if everything is fine and recording. Yeah, everything is recording. For a single phase half wave rectifier controlled rectifier with RL load, which of the following statements is true? Load current will be continuous for firing angle 0 only. We have just solved for RL load. Load current be ever continuous, right? No. Why? Because the amount of charge, even if alpha is 0. So let's say if alpha is 0, and if I go back to the analysis, of single phase half wave rectifier, control rectifier with simple RL load, and go back to the waveforms. So even if alpha is 0, so it will conduct till for the first half cycle, the current will increase, and for the next half cycle will be what? Current will decrease. And you might say, sir, whatever it has like energized, it will de-energize within the same period. No, I have specifically proven that my beta will always be less than the discharging time, right? So my discharging time will always be less than charging time, so it will discharge more faster. Hence, obviously, for some period of time, the current will be 0, and hence load current won't be continuous. Okay, load current won't be continuous. So continuous means continuous conduction. That means it will never go to 0. So this first statement is specifically wrong. Okay. First statement is wrong. Next, average voltage across the inductor in one cycle will be 0, correct, right? This is the volt second criteria that I derived in the previous lecture. Average power delivered by the source will be equal to the average power dissipated by the resistance of the load. Is this true? Like they talk about the average power. So generally, right, what the problem is here, average power in terms of the naming is a bit misleading, because generally we define average power as the overall power, right? The active power. So in this case, specifically average power, I should write is the, okay, we should not write this average power because this term will be wrong. I will say the DC power delivered by the source will be equals to load, because PDC is defined, but average power is defined as basically overall whatever active power that the source is deploying, and in that, right, the DC components are present, but always also the AC components are also present, right? So that is the case. Next, the DC power delivered by the source will be equal to the average power dissipated by the resistance of the load, which is correct, right? So basically, what does this tell mathematically? Mathematically, this tells us this, right? So basically, PDC will be equals to IO average whole square into R. Okay, and that is correct, right? PDC supplied will be equals to this only, because there is no other because inverter doesn't store any energy. Okay, and this we are talking about RL load, so we don't have any battery as well, so all the average power will be dissipated through the resistor, which is correct. The DC voltage of the RL load will be lower if instead of RL we have a pure resistor. This is correct, right? This is correct. Why? Because we get some negative voltage as like SCR is on even after omega t equals to pi, because after omega t equals to pi, my Vs goes to negative and my Vo also goes to negative. So overall that will reduce the average voltage, right? Because my output voltage is negative for some point of time. So if it was even on for the whole first half cycle, for the second half cycle it will be on, and that voltage will be negative. That will reduce the average. So obviously this is correct only. This is correct only, but this problem we rectify, we resolve this problem with the help of a special diode named as freewheeling diode that we'll learn in the next lecture. Now, next question is this again theoretical question. For a single phase half wave rectifier controlled, okay, this is not rectifier again, single phase half wave controlled rectifier with pure inductive load, which of the following statements is true? So this is also the like another theoretical question one. So load current will be almost continuous for firing angle equals to 0. This is right. Almost continuous means just on the edge of continuity, and this is true, right? So it like SCR always conducts just at instant omega t equals to 0, omega t equals to 2 pi, omega t equals to 4 pi. It is just turning off for an instant, then again it is turning on. So boundary, it is on the boundary of continuity and discontinuity. Discontinuity. Okay, so this is the case. So hence this is correct. So because I derived it in the previous lecture only. Now average voltage across the inductor in one cycle will be 0 for firing angle equals to 0 only, which is wrong. Average voltage across the inductor in one cycle will always be 0 if I trigger this here at omega t equals to 0 or omega t equals to pi by 2 or whenever, right? Whenever the average voltage across the inductor will always be 0 if the inductor is reaching steady state. So this is wrong, because it is saying only when the firing angle is 0. No, it is for all the cases, for all the values of firing angle, the average voltage across the inductor will be 0 according to the volt second criteria. Converter will operate in two coordinates, which is correct. It is delivering in the first quadrant. So from 0 to pi, the power, right? Power flows from what? Flows from source to load, and from pi to 2 pi, the power flows from the inductor, that is load, to source, right? So obviously this will operate in two quadrants. Maximum conduction period of the SCR will be 2 pi. Maximum conduction period of the SCR can be 2 pi. Yeah, it can be 2 pi because if the SCR is triggered at omega t equals to 0, right? If my alpha is equals to 0 degrees, then this condition can happen. This I derived in the previous lecture only with a simple diode. So we can replace it with a diode. So that's it basically for this lecture. I hope you enjoyed this lecture. We learned a lot. Okay, and up until now I was going slow, okay, and in this lecture I went fast because why? I was building up the foundations, right? I was building up the foundation so that you can understand everything what I told over here, right? That's why we were slow initially. Now we'll ramp up the things. Now we'll pick up speed because I have explained you a lot of concepts that will be helpful to clear out your basics. Now we'll understand everything smoothly. Thank you for watching, and I will see you in the next lecture.